Hey guys, welcome back. We're doing a video on exponential graphs. We've already covered exponentials just a little bit. So to open up, we're going to talk about the general form. Remember that it looks like the function of x is some number times by the base to the power of the variable itself. So the variable is what's changing throughout that function. And we've got a few little details that we want to add on here. B's got to be greater than 0, otherwise it's not a whole lot of a function. I might try and show that a little bit later in the video. B can't be equal to 1. Again, same reason. If B was 1, then it would just be a straight horizontal line where A is. And then A is also not equal to 0 because, again, it defeats the purpose of the exponential function. So the simplest exponential you're going to look at is y is equal to 2x. Y to the power of x. 2 to the power of x. There it is. Okay, this is probably the most basic, although the most common is when you use Euler's number. We haven't really spoken about Euler's number a whole heap, probably won't for a while, but that's more commonly used than, say, this, for various reasons, but the simplest one's going to come from this. Let's do a quick table of values, and we're going to take a closer look at what this particular function looks like as we plot it. So our base is 2, so we've got 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of, or 2 squared, or 2 to the power of 2 is 4, okay? And each time we increase x by 1, that number y, f of x, is going to be doubling. So 8, 16, and 32. Pretty straightforward so far. Okay, and let's take a quick look at the simple graph here. We have at 0, it should be 1. Okay, at 1, it should be 2. Not going to be perfect, I'll show you again electronically. 4, 8, 16, and 32. Okay, and a smooth curve needs to go between those. Don't rule lines between each of them. I'm just going to turn this upside down so it goes with the wrist. Right, and on the other side of the y-axis, it's going to still be decreasing. Okay, so something like that. Okay, again, it's not going to be a perfect function, which is why I've prepared this a little earlier. Okay, we have, move me over there. We have our function y is equal to the 2 to the power of x, and we have several points which I've plotted along here. Same table of values that we've done here, just with the 6th one on here as well. Don't need it really. And I've changed the view window so we can see those plots. That's what our exponential looks like, basically. Okay, what we want to look further at is the general form. What all exponentials look like is something like that. Okay, so there's going to be two types of exponentials that we need to be very aware of. They can either indicate growth or they can indicate decay. Okay, growth is going to look like it's increasing very fast, and decay starts off this side quite high, and then as it hits this value, it gets closer and closer and closer to 0, but never actually touches. You might remember that when we have that not touching but getting close to, is called an Okay, and that's at y is equal to 0, horizontal asymptote at y is equal to 0. I detail it a little bit down here. Anyways, growth increasing constantly, decay decreasing constantly. Okay, that rate of change, that slope, would be gradually decreasing with the decay, but it would be gradually increasing, that curve, increasing as it goes around. Okay, when we have this type of graph, or where we have it, is when we've got our exponential function but b is greater than 1. Okay, you've got to be multiplying by a number larger than 1 to increase it. Whereas to decrease it, we've got a number between 0 and 1 not equal to at either side. Okay, we don't really do exponentials where that base is negative. I will address it at the end of this video. So, in both cases, generally speaking, the y-intercept is at x is equal to 0, and meaning that when we have x is equal to 0, you've got b to the power of 0. B to the power of 0 is 1, leaving us just with a. So whatever that number is in front of the base with our variable here is usually our initial value. Okay, unless you had something added on or something around this, then that's what our initial value is going to be. All right. And as I mentioned earlier, that horizontal asymptote exists at y is equal to 0, again, unless that exponential function has been shifted up or down. Anyways, a big part of this exercise that you're going to do is describing features of a graph. Now, this isn't in any particular order, but we're going to, when asked to describe features, intercepts is probably the easiest one to take a look at and always address. Both x and y intercepts are important. We could talk about whether it is increasing or decreasing. Sometimes it's both at different points in time or different parts of the graph. For our exponentials, however, you're just going to have the two types. Any asymptotes that might come up, any local minimums and maximums. When I say local, that's usually when our domain's been restricted. Okay, and if that domain's been restricted, then it might not necessarily be in the maximum of the function overall, but just what we can actually see of it. Whereas global is whether it overall. And we can talk about local and global minimums and maximums, and it could give us a better idea of what that graph is doing. Range and domain, useful features to address, okay? And you might also talk about long-term trends, such as when x is going to positive or negative infinity, what's happening to that function, okay? There are others. Any other interesting features you might like to address, there's nothing wrong with adding them on. You could talk about symmetry. Gotta make sure that I do 2 m's of symmetry. Symmetry and such, so there might be some sort of axis of symmetry around the place that you could address, usually with your parabolas. But that's generally what's meant by describing features of a graph. Addressing those when, where it happens, how much it happens. Okay. As for the video, that's pretty much what we need. So this is our focus here. Growth when b is greater than 1, decay when b is in between 0 and 1. Okay, we have our y-intercept at 0a. Again, that's when it hasn't been shifted. That's just for this function. Okay, it could be shifted up or down, and that might change things a little bit. And that's about it. Let me know if you've got any questions, and we'll see you next time.